Let me go ahead and share my screen really quick. So in our principal business meetings, we've talked a lot about how many of our talks are on the more advanced side. Um, so I'm going to try to keep this one simple. So this is going to be a beginner talk about serial bus servos and how to use them. To start, I'd like to just briefly, hint about some things you're seeing in the news. Honestly, I'm thinking of proposing like a 5-minute what's new in robotics thing, just because there's so many breakthroughs happening so often. But these types of developments are at the forefront of robotics and humanoid robotics today. They are low gear reduction, brushless servos, which aren't super expensive now, but they're not cheap, or a variant for linear motion. Oodles of processing power. But when you look at the hardware, you're like, okay, it's probably going to be a minute before I can, get approval from the missus or the mister or, from your bank account to do it. But it's simply amazing. Um, and this is state of the art right now. I'd highly recommend you bookmark it and check it out if you haven't already. There's no less than 12 or 14 companies dropping hundreds of millions and billions of dollars into developing humanoid robotics now that these large language model derivative type control regimes are starting to show promise to do real things. So it's kind of the perfect time to be alive if you're a roboticist. About 10 years ago with my InMove robot, which is built just using off-the-shelf servos, I had realized over the course of the project that servos were pretty much a dead end from a robotics standpoint. They operate open loop. You send them a command pulse, and eventually they'll get there at some speed, at some acceleration. And when they get there, the dead zone is between 2 and 4, plus and minus 2 and 4 degrees. So they're not accurate. You have no idea where they are. That's why if you build something complicated with servos, when you turn them on, you have to give them a control pulse to tell them where to go. But if you don't know the initial position of the robot, you get the spazzy stuff, right? So I'm sorry. Yeah, we do for there's no HVAC, so we need a little bit of airflow. I'll broadcast a little bit. Is that better?
Maybe 1 or 3 better.
Okay, we can try that.
Yeah.
Oh, those were the lowest speed. Yeah. All right, so it's a balancing act. So if it starts to get uncomfortable in here or a little bit too warm, we'll kick it back on. But yeah, we're just trying to make it work with no vents today. So I've kind of written off servos. Like they're fun to do lots of interesting projects, but for quote unquote serious robots work, it appeared to be a dead end up until about 4 months ago, when the mobile Aloha folks made some waves by demonstrating a robot-like mobile device that through training through teleoperation is capable of doing things that we just couldn't do reliably. You can program a robot to go through any set of motions. Industrial robotics is exactly like that. But in the real world's messy, and unless you're on an assembly line in a work cell with well-defined, input and placement parameters, it is just working. Now, this robot is the Aloha Mobile. It's a mobile version of the Aloha platform that's trained through a combination. It uses deep learning and recording off of 3 cameras, 1 on each hand and 1 in the head, and recording through teleoperation. So, they go through the process of cooking shrimp 100 times, 50 times. They feed all of that into a deep learning training, and they train it. And through the magic of neural networks, it's able to extrapolate and perform that task, even when things aren't exactly where you left them. It's simply incredible. This caught almost everyone off guard, including Tesla bot and including everyone else. I have another video link in. So this is a dedicated YouTube video that Ben will paste in the chat, showing fully autonomous behaviors. Right now, this platform is relatively a robotic. All right. They said that they built it using off-the-shelf components for about 35,000. Now, 35,000 is unheard of for something this capable. I hate to use the word cheap, but when you're looking at like Willow Robotics, you know, and they're $150,000, $250,000 robots, it was incredible. Still out of my price range. Trosson Robotics is actually offering Aloha research kits. They keep updating their page. I think I saw a price on this when I checked last night. So, you know, and it saves you the hassle of ordering the components yourself. And as amazing as that is, it's still not in my price range, right? But it proves something. It proves that servo or servo derivative mechanisms are capable of doing useful work. Servos are back on the table. These are servo bots. These Dynamixel arms, these robotics arms, the ones that you see on the platform are, sorry, are about $7,500. Still out of my price range, but they're really coming down. Dynamixels were the first folks to come out with this concept of a serial bus servo. There's a bunch of stuff that makes them different. But they're higher resolution feedback, they're stronger, they're modular, and actually I think one of my first robotics kits was about 6 of these, and it was like a couple $100, but it was a lot of fun. But for the larger ones, the heavier, the more capable ones, it's still out of a lot of hobbyist price range, people's price range. However, a couple other companies have risen up to offer low-cost versions of these. They're not drop-in replacements. They're actually extensions of existing servo sizes for the most part. But we go from $40 for a decent servo, and these guys offer all kinds of ranges, to $15 to $20. And so that got me thinking. So PTech is, I only know about 3 right now. PTech's one. High Wonder is another manufacturer of serial bus servos, the servos that are used in the mobile Aloha platform. And the ones that I'll focus on today, WaveShare. So what got me interested in this project was someone on the HP robotics side had mentioned that WaveShare had a low-cost robotic arm that was kind of similar to the Dynamixel arm. It's like $190. So it's not cheap, but you know, I think I can swing that and not have to start for the next couple of weeks. So it got me thinking about what I call it a wish.com version of the Aloha mobile platform would be. And since then, it's evolved to something that only vaguely resembles the Aloha mobile platform. But after about it seems like forever, and it seems like yesterday. Exactly 2 months after I had the bright idea, I was able to string together off-the-shelf components. So we got the 2 arms. No. Let's just trying to remember how the screen works. There we go. Right, the head, the camera, the Seat Studio directional mic. I did have to design some brackets and some 3D printed hands, an off-the-shelf USB speaker, and the motorized base from WaveShare. I have something that my intuition tells me could be almost useful. Now, is it tall enough to reach over countertops? Unfortunately not. So I'm going to put useful in air quotes. So useful like secure maybe. both in terms of its hopefully capabilities as well as its height and its strength. So, the servos I want to walk you through today in this beginner talk are the servos that are used in the arms on the WaveShare robot. All three of those manufacturers use a similar form factor, and this servo is one I have on my desk, and we'll at the end of this talk we'll go through interfacing with it in Python, and we'll talk about the differences in how you control it and some of the things that make the servo really awesome to work with.
A lot better than the standard old ones.
Yes.
With the and feedback and all that.
Oh yeah, don't worry about this one. Sorry.
I used to use old thumbs.
What's the mechanical connection on that? Or the screw head itself?
Oh, the horn? Yeah, the horns are connected just like on standard servos, where you've got usually a screw and then it locks in with the teeth on the third heel. All right, so in this super fancy presentation here, just to compare some of the difference between them. I'm not bagging on servos like you shouldn't bought them. They're a lot of fun. They're super cheap. I've done some really amazing things with them. But here are some of the reasons you might want to convert your future projects to serial bus servos. The first one is feedback. You use the servo object if you're using the Arduino, and then you set it up, and then you send it an angle, and that angle gets converted into a pulse, and it gets sent off in the background, right? So you can send off whole degrees using the standard servo library. But once you fire off that command, you don't know when it gets there. You don't know how fast it's moving. You don't know its velocity, acceleration, or instantaneous position. You don't know if it got stuck. You don't know if it's already there. The commands are fire and forget. And that's why when we talk about servos, we talk about open loop control. There's no, the servo internally operates closed loop. You give it a command and it meets it. But as you send it commands, you have no idea what the status of the device is. And that gets really frustrating. From the nerve-wracking moment when you power up your little device and you send it its first motion command, hopefully it's not going to swing its arms around or flip over or anything. To anything more than scripting motions, it's really hard to do anything useful, productive with a servo when you don't even know where it is. You can script motion, but it gets frustrating. With these serial bus servos, boy, howdy, do you have information. This serial bus servo operates as a device on a serial network. Now, in the background, it communicates over a serial bus using packets of information. You don't even really need to get into that, but it's two-way communication. You can ask the servo, hey, servo, what's your position right now? And it'll tell you. Hey, servo, what is the temperature of the MCU in it? Are you overheating? It'll tell you. Hey, servo, indirectly, based on the amount of current that's being consumed, how much force are you applying? What's your speed? What's your current acceleration? And it will tell that back to you, which opens up all kinds of control regimes and ways of interfacing with the servo. So not only do you get the instantaneous position, you get a whole list of other information. And I'll just really briefly show you to it a little bit. But you get to communicate with it, and it'll tell you exactly what's happening in the servo. Now, in servos, most of the time, their position is being managed with a potentiometer. Potentiometers are great. The Sony Aibo, a very performant robot dog, use potentiometers in the joints. But potentiometers, if you've ever pictured one or seen one in hand, they can't rotate a full 360 degrees. They're at most maybe 270. And then if you force it past that, then bad things happen. For serial bus servos, almost all the time it uses a magnetic encoder that does two things. First off, generally speaking, you get a higher resolution positional feedback. I think down here below. When you're working with servos, you're lucky to get plus or minus 2 degrees when you say, hey, go to 175, which is still kind of a round number because it's not precision. You never know exactly where it is. The serial bus servos use a magnetic encoder with 10 bits of information. So you have a 1023, 1024 positions. You divide 360 by that, your angular resolution is about 0.35 degrees. That's something you can work with. Generally speaking, serial bus servos will be stronger. On the micro side, on like the MG90 side, they operate on the same voltage, so they're probably about the same. But this serial bus servos, they're sitting up there, they're 12 volts, so they're already a lot more powerful than 12 volt standard servos. And the big ones, I believe, go up to 24 volts. The ones on Alfie are all 12 volts. I have an asterisk here for magnetic encoder. Highwonder does make some serial bus servos with a traditional potentiometer. I think it was a cost reduction measure. The wave share servos all have a magnetic encoder. So not only can they spin a 360 degrees full, you can tell the firmware that there's a gear reduction in place. So if you tell it that the gear reduction is 2-to-1, it'll then interpret your position command on the basis of that gear reduction, which is pretty cool. They're both fast, and to be honest, they're both cheap. Cheap for servos can be $3 to $5 and $7. These servos are about 20, so they are more expensive, but still well within the range of hobbyists like me.
I'm just curious, do they use continuous rotation
Yes.
with velocity?
With the magnetic encoder versions like these, they are capable of continuous operation. So you have not only positional control, but also velocity.
Okay, cool. 'Cause the Dynamixels had that, but there was a gap in the encoder, so like there was like one, less like a fifth of it didn't have any encoder on it. It was kind of weird. Yeah.
So yeah, Ben will be kind enough to post these links in case you'd like them in the background. So WaveShare has product pages and wiki pages for all of their products. So good news, bad news, they're super cheap. And there is documentation about everything you need to know. But because they're so cheap, it's not as slick as the Dynamixel documentation. So it's a little bit easier to dive in with the Dynamixels, even though they're the exact same type of a product, just because they spend a little bit more money on documentation and software. But everything is available in their product page and wiki if you're patient. Here, let me see if I can a second.
Yeah, I was thinking they mentioned the wiring. He's gonna get to it. Yeah. I remember this. I'm excited.
So there is documents about the protocol. It would be fun to read through what that was, but to be honest, to get started, I would ignore all of that. But they document in detail. The protocol is actually the same between Dynamixel and the other ones. For obvious reasons, they probably just copied. But their memory location map is a little bit different. But it's the same general gist. Now, for today's demo, so in order to run one of these servos, you need a couple of things. The servos are serial servos, so they need power and ground, and they have a signal line for the serial protocol. For today's demo, and this is all sitting on my desk, I'm going to use this $5 serial bus adapter. It plugs into your computer over USB, and it supports 12-volt input through dedicated lines or through barrel connector. And it also has a UART if that's the way you want to apply. And then it's got two of these connectors, which are standard, but the name escapes me, to plug in servos. With the wiring they provide for their serial servos, they say that you should limit the number of servos you plug in serially to 5. That's not because of communication limits. It's based on the projected maximum power draw of the servos and the gauge of the wire that powers them. So,
Do you mean 5 per each of those? Or 5 for this board?
5 for each string, for each wire, yeah.
5.
Yeah.
Amps,
Up to 5 devices.
5
But
devices.
even that, I don't think that includes running 5 devices
Right.
at full lock, right?
Or
There's,
5 devices at nominal.
yeah.
Nominal.
Yeah.
Current.
Yeah, so the way I got around that on Elfie is at the elbow, I split off the power lines and I have a separate power line that goes up to power the lower half of the arms. But there's one single serial line that goes all the way from the shoulder down to the.
Right,
it's a
you
little bit-
split off the power.
Yeah.
Which you can always, we always need to do almost.
They
Yeah.
all go into the bike battery.
Yeah, so all of those go into a power distribution board that I am both proud of and afraid to show you guys. And that distribution board goes in, is fed by a buck converter.
Oh, yeah.
And then that buck converter has they do a 5 amp, it's probably a 5 amp fuse in line with the battery. So direct battery protection in case things get weird. And that's 5 amps at 38 volts. And then there are 2 other fuses that are run all the way up into the head with the switches, because you want to be able to access them. So I have a separate fuse block protecting the electronics rail and a separate fuse block protecting the drag rail. And I just ran lines up through the body into the head to make it easier to get to in case things get weird. But yeah, power, when you're working with things like this, very important to think about. Just because you can plug something in doesn't mean yeah, put a little bit of thought. So we'll use this $5 adapter. It's sitting on my desk. I had some power bricks that came with the arms that I plugged in, and then I got one servo plug.
It's much smaller than it looks on the computer.
Yeah.
Like I picture that being Arduino size, but it's like,
Is it 1 inch?
it's tiny.
Yeah, it's tiny, tiny.
1 inch across?
Put it in your hand in the camera, so
Based on that, so.
like side buttons.
Oh.
It's very little.
Yep. All right. And just the weak key for the bus adapter. Now, between the weak key for the bus adapter and the general driver and for the servo, there's a bunch of links. It's not super coherent, but if you browse through all 3 resources, you'll find everything that you need.
You know, if there's like a Arduino library. Old school.
Yeah, actually there is. Yeah. Yep, there is. So yeah. So
He's working in Python.
Oh, I see. So, yeah, C, yeah, like for C,
Yeah.
you know.
Yeah, absolutely. There's the vendor provides an Arduino library for control through an Arduino or any type of a low-level device. And that's what I'm writing for the brainstem portion right now, because they're run by ESP32s. For the purposes of today's demo, I have the board plugged into a Windows computer, and we're just going to do a Hello World equivalent application in Python, just to show how it works. But yeah, it's fully supported. The library is not pre-compiled, and much like the Python library, I'm finding myself making changes and updates to extend the functionality once I get my footing. Don't worry about any of that. We're going to use all the standard functions for today. So, all right. So with that as an introduction, let's arrange ourselves right here. All right, so I have a camera set up. I've already downloaded their ST Servo Python library. And that library is divided into 2 parts. They give you some examples, even though they don't clearly state it, about how to use the servo. These are just straight Python. We'll look at them in a second. And then when you want to get really down into the weeds, the low-level stuff is all in their ST Servo SDK object. And so these are the mechanism by which it leverages that serial protocol to allow you to do interesting things with the servo. So here's how I'd like to approach this. I'd prefer not to spend a lot of time draining each slide, but I want to give you the feeling of and the intuition of how to work with this and how the servo works and how you'll work with the servo for your next robotics project, because I'm pretty sure by the end of this talk, y'all are going to switch to serial bus servos. All right, so the first thing I'm gonna bring up here is ping. For those of you as nerdy as I am, you know that ping means I'm just gonna say hello and that device is gonna say hello back. We do it on computers, on the internet. I think it's a poke on Facebook. Do they still poke people on Facebook? I don't know these days. I don't use Facebook much anymore. All right, so here we have a whole code, a whole program. Now, I'm gonna fancy this up a little bit. I want to copy all of this and I'm doing my coding in Visual Studio. If you have a favorite IDE for Python, that is totally okay. Most of this will still apply to your IDE of choice. I happen to think Visual Studio Code is one of the best free IDEs available on the planet everywhere forever. Aside from context, right-click, highlight, surfing through code, autocomplete, integration with Microsoft Copilot, remote access. It also supports Jupyter Notebooks, which is a really fun way of creating and interacting with Python scripts. And so I'm still going to call this a beginner because I think this is a valuable tool to add to your arsenal. So what I'd like to do is open up and create a new Jupyter Notebook file. And I'm just going to paste all the code, which you can do. That's fine. That's fine. Now, so why even use a Jupyter Labs notebook? Well, when you write a Python script, and every time you save it and then you run it, right? That's the cadence, right? Save, run, crap, and error. Save, run, crap, change a variable. Which works just fine. And you can do that through Visual Studio Code. Once you tell it what Python interpreter you want to use, you can run the code directly through here, and that'll work just fine. So, but I am going to move this into Jupyter Labs just to show you some of the benefits of that. Now, right now we have one code block from top to bottom, and the same thing. I can click on run, and it'll run just fine. But there's one thing we have to do first. The serial driver board is plugged in to the computer through USB. As of right now, we don't know what COM port it's on. The serial UART shows up as a COM port, both in Linux and Windows. So let me show you how to figure that out on the Windows side. So we'll go to this PC, right click, show more options because we're on Windows 11, and manage. I thought I had this open, but it must have closed. So we'll go to device manager. We'll get a warning. We're not logged into the admin, so don't trust myself not to screw anything up. That's okay. And then what we're looking for is ports, COM and LPD. This is the only part that's a little bit weird. At some point, someone will think of a faster way of doing this. But I need to know what the COM port is. So let me open up ports. And I can see that that driver is showing up as COM3. So now I know where it's hiding. You could also go COM1, run, crap, there's an error, COM2, crap. That would also work, right? But to be legit, open up device manager, and then once it's plugged in, you'll see it show up here. All right. So that's our ping example. Let's start separating these out into code blocks. So I'm going to put the cursor right here. We have a whole bunch of comments, which is nice and it's pretty, and then we have some reports. I'm going to put the cursor right there. Right click, notebook, oh, wrong one. Right click, notebook cell, split cell. All right, so now we have a cell up on top just with comments, which can be evaluated separately, but there's nothing to do. And then we have a second cell down here. So we're going to start splitting our code into sections. And what's nice is that once a section is run, it stays in memory. It doesn't exit out and release everything. So you can iterate more quickly by separating your code into sections and then Evaluating them separately. So we have a comments right here. We've got some setup. I'm not going to go through any of this. I don't even really care how it works. It looks too complicated for what it's trying to do. But I want to put that in its own section. So go to cell. There's probably a keyboard shortcut for this. And split cell. All right. So we do have some setup here. So I'm going to run the cell just on its own. Click on this little arrow here. It says execute cell. And it's done almost instantaneously. So we do a couple of setup functions, and then we import that Servo SDK. Now, in the next row, it looks like we have some setup. We have a constant STS ID, 1. That's the number of the servo that we want to communicate with. This is one of the coolest things about this, is that you can string these in serially. Each servo has their own ID. And that's something that you set when you first get it, and you can run a program to set that. So that you can have 5, or in this case, 7 servos all on the same serial line. But when you communicate, you're like, hey, servo 1, what's your position? Hey, servo 3, move to this position. Because each servo knows its own ID. And so the one that I have on my desk here is ID 1. So we'll leave that.
The second code, is there an app to do that too, or?
For Dynamixel, they do. For the cheap ones that haven't written the app yet, you write a little Python program. Okay, to swap it. Yeah, I'm skipping over a few of the things that are a little bit.
Change the ID.
Yeah, change the ID. It's not hard.
It's much like CAN, you know, like the same thing. You have CAN IDs, you have to set them all.
Exactly.
Remember, and write it down.
Exactly. The second one is the baud rate. So your devices have to agree on the communication speed that you're going to talk to them with. If they don't match up, you guys aren't going to understand each other. By default, these guys are set up to communicate at a megabit, which is actually, it's a lot of bandwidth. So we're going to leave that as the default. And our third constant here is what COM port we're using. We'll change this from COM11 to COM3. And then let's see, some more boilerplate. There's something that opens up a port. We succeeded or not, set port baud rate, set it or not. So this is just more setup. So I want to put another break in right here, just to separate out the code. All right, so if everything's set up correctly, this block of code sets up and opens up the communication port to that servo port. So let's run it. Oh, and that's it. We opened up the port and we changed the baud rate. Very good. Okay. So this third section of code. What's also nice about this is when we go to the next one where we go through how to move the servo, 3/4 of that code is the same. We're not going to have to copy the whole thing. We'll just copy the meat of it. All right. So what do we have here? Copilot's offering to be helpful. Not helpful right now. Hey, guys, a minute, yeah. Grab over here.
Yeah, this is fine. Thank you.
All right, so without going through and trying to figure out what this code does, it looks like it attempts to ping the servo. And if it's able to, you get this message, ping succeeded, with nicely formatted. And if the error object that it passes back isn't a 0, it'll show you what the error is. So let's just go ahead and run that. We'll see what happens. All right. Ping succeeded, SDS servo number 777. And then finally, the last thing that it does is it closes the port. Let's separate that one out as well.
How do you do that? You just to split the cell, you put the.
I just
you're
put
just
the
doing the
cursor
cursor at a point and then split.
Right click, no put cell, split cell.
Oh,
I'm not
okay.
smart enough to memorize the keyboard shortcut.
Everything below that gets split and then you.
Yeah, upper and lower. And what's nice is we can go through and we can run each of the individual pieces of code separately. So that's what makes this a lot of fun. Let's go ahead and save this so I don't lose it. All right, so there's a lot of boilerplate code. I don't care about what most of it does. But this is kind of your hello world example, just to make sure things are set up correctly. Now, and of course the servo doesn't move because we haven't told it to do anything. Let's look at another one of their demos called Right. And we'll scroll through a lot of the same boilerplate. We have some different values here: minimum and maximum position, moving speed, and acceleration. And then, so this one definitely moved it. So let's do this. These guys, let's just copy that. And let's add that underneath here with the rest of our stuff. And port handler, blah, blah, blah. Okay. And then it does something. Let's grab the does something part. And paste that in here. They've got some goofy press, print, blah, blah, blah. I don't care about that. Let's comment that out. All right. So we'll rerun the section that defines those new variables. Working with nothing. Okay. There we go. All right. So just reading through this demo right off of their website, it looks like we write a position. And then if we get a success, awesome. And then if not, we show you the error. And it switches back and forth between two goal positions, which are the minimum value and the maximum value. It's a little convoluted way of doing it, but that's all right. It's there. So, right position X. Let's take a little bit closer look at that. So this is another it's a good point about serial bus servos. So for their right position X, when you talk about servos, you just give it a position, fire and forget, maybe it gets there, maybe it won't. These guys are a lot more advanced and not complicated, but they have a lot more capabilities. So with that goal position, you can communicate three things: where I want you to go, how fast I want you to move there, and how fast I want you to accelerate there, right? So this is very similar to the control method for the brushless servos for the humanoid and the dog robots. Their controllers always accept, and you can do it by velocity or force as well. But when you're communicating these, it wants to know where you want to be, how fast you want to go, and how fast you want to accelerate with every command. So you have control now over how fast you want it to get there. And as part of your control regime, how you choose to control your robot or your arms, you can take advantage of that. So you can program in, hey, if I'm moving something heavy, move it at a slower speed to this position. Or in my robot's case, I'm very top heavy. So when I'm starting to move, start to move slowly. We use a slow acceleration so you don't topple over. But that's one of the many cool things about serial bus servos is that whenever you command it to do something, you give it all three pieces of information. And then when you get a little bit more advanced, you can pull that motor and see exactly where it's at. Is it there yet? Is it still moving? What is its speed at? What is its current position? So cool. So cool.
Is there like speed ID type control
in
in there somewhere, or you?
Yeah, there are. Let me see if I can. Here is, and this isn't something I would worry about when you're first getting into it, but all serial bus servos are set up like this. They call it a memory table or a memory map. I think it's because the initial ones were 8-bit and they wanted to simplify it. But your communication, your low-level communication with the servo is by reading and writing values to these memory addresses. And Some of the memory addresses are, each one's 8 bits, 1 byte, but some of them have 2 locations for 16-bit and some of them only have 1. And so just scrolling through here, we've got some easy ones, things that you would only read, right? The firmware, major version, sub number. Now, here's the fun one. When you change the ID, you'll be writing a change to this memory location to change the ID that the motor responds to. Baud rate, return delay, most of those you won't touch. You can define minimum and maximum angles in the firmware so that if you command it to exceed that, it won't exceed it.
You don't have to put that in your code.
Exactly. You can tell the servo, and the servo will help protect you. There's a temperature limit. I don't know what it's set as a default. It's 100. To say, hey, when the servo exceeds this temperature, shut down. And it's already baked into it. It's already baked into that. One of my first projects, I was overusing a servo in the head for a head that was altogether too heavy. And in the wrong position, it would overheat and it would shut down before there was any damage. Traditional servos, they'll catch fire. They don't care. There's
They have clutch ones that I
Oh,
bought.
really?
I bought DF Robot clutch servo. They show the guy holding the servo in you know, a 9 gram and like twisting it while it's on. And then it basically clutches and it's not broken.
Yeah, I've probably
Those are
set
cool.
fire to about a dozen or more
Actually,
servos
fire?
in my life.
Oh, because it heated up.
Because there's no checks and balances. If
Yeah,
you
that-
command it to a position that it can't reach because it's stuck,
Yeah. That's
it'll
like,
just go at it.
so I have a clutch one and I commanded it to a place that the cable was caught. And it, for a couple of seconds, it stayed there and then it just de-energized. It's really, I bought those on a whim a long time ago, but clutch servo, that's.
Yeah. Yeah, so these guys will not overheat. When they hit your temperature, they'll just shut down. Probably not super convenient if you're doing something important, but at least you won't have to replace it. You can define a maximum torque value to say that torque values over this amount, it won't honor. Just all kinds of stuff. You can define custom PIDs for the internal control right here. I haven't looked into that yet,
That's internal.
but they are available, yeah, to control how it. Minimum startup force, counter instance of protection current. Most of these I don't know where they are. Protective torque, speed closed loop, PI. Yeah, PNI. Target location, when you send it to a location, these are the 2 values that it populates. Running time, running speed, lock mark, is it currently moving? Current load, current load as inferred by the power that's being drawn across the driver. Turbo status and current. So yeah, all these are available to you to understand the state of the servo. But the short answer is, yeah, they do give you the ability to change those in addition to the velocity acceleration curve.
Yeah.
All right, so we've got everything opened. Let's look at a little bit of a code right for the demo. We're basically writing 2 positional values. And then, yeah, let's run it and see what happens. Yeah.
There it goes. It's opening port. Opening ports always takes.
Oh, because I broke out of it. Explosive part. But there's no air.
We just saw it move.
It's the caster version.
What?
It moved right when it canceled it.
Oh, that's,
Oh, I think
oh, port in use. They tried to.
I think I know what's going on. All right.
Did it open twice?
There you go, okay.
Serial ports
Let's clear all outputs.
can be nasty. Because it like gets stuck.
Our bottom one was closed port.
And don't close, I know, yeah, that's.
Yeah.
I always had that part, but you control the
C
safety
handler,
stuff.
sorry, when you control C, it closes. I put that into all my Python, you know, if it interrupts, then
They close things.
and close whatever, not just servos, any serial, anything that has to be closed. So that control C always does the cleanup.
What's going on, buddy?
Shouldn't, not that, that's part of it, wasn't part of it. In that one block.
No, that's only at the very end.
Oh, yeah. Oh, there it goes. Oh, what did you?
What's going on? What did I mess up? So I blocked out these.
What does it say?
I didn't think the port was still open and then it finally timed out, it sort of worked.
Yeah, something like that. Wait, but now you'll have to start from the beginning. I think you might want to start from the beginning,
Yeah.
like let it cancel out and then start from the beginning, open port and. Oh,
Yeah.
oh, then there's that. That's the, that kernel thing can get confused.
All right, so let's get rid of this first part right here. We'll just delete it out. While one, right position X, clear all outputs. Let's just do a run all.
Oh, what breaks it? It doesn't.
Oh, I know what's going on. I know what's going
How come it's while one?
on. I know what's going on.
Oh, it's supposed to just do an infinite loop there, right?
Okay, yeah, this is a little embarrassing, but it's an infinite loop.
On purpose.
And this little piece right here, press any key to continue.
That's important.
That is the break that gives it a chance to move before you move to the next step. So,
All right.
I think we're,
Yeah.
let's say, I did
Because
something.
you're giving it continuous commands, aren't you?
Yeah,
About that.
yeah, that is why you don't make last minute changes, right?
We just learned something
We all learned something.
about
Alan isn't nearly as smart as he looks.
No. Purely programming, or can you press? You have to take keyboard input, you know. In Jupyter.
Yeah,
Does
you know
that
what?
work?
Yeah.
Is there a way to do that?
Let's do
You could just do a sleep, right, or wait, a delay, or in Python, a time dot sleep.
Let's try that and then we'll just move back to a normal one.
You can put it back in the same way. Yeah, I mean, but for
But
this,
it's not made
for Jupyter Notebook though, you can't have it like get character, can you?
Do we have a delay in Python? I don't
Yeah,
think so.
time dot delay. I'm sorry, time dot sleep, and import time. If you didn't import it already, and then you give it a number in seconds, so,
Seconds?
yeah, so whatever, like 1 second, and
Yeah, let's
however
try
many
it.
seconds you want.
Let's say a few seconds.
Yeah, it's a few seconds. Of course, that'll wait on the first time 4 seconds. There you go.
Hey! Are you not entertained?
Go back.
All right, so yeah, sorry about that. That was all self-inflicted problems. So it's writing the following two positions with this velocity and this acceleration. And again, these are just demo programs to give you a feel for how to interface with the servo. But the servo just isn't a dumb device like a standard servo. It's an intelligent peripheral. And step one is aside from your hello world and sending commands, is to come to terms with having control over the position, velocity, and acceleration for all of your commands. And then once you get a handle on that, then you can start setting up more state machines to be able to read back the instantaneous position. If you've got a more complicated robot and you have like a visualization of the robot in ROS, like RViz or Voxclub.
Hey, how's it going?
Hey, goodness, so good to see you again. It's been too long. Good.
I want to comment how smooth that's running compared to a regular server. Regular server like jump over and then like at the end and just all the nastiness. That's so nice for a robotic.
Yeah, this is I know like an hour of prep to watch a servo thing, but like to keep it as beginnerish as I can, like this gets your feet wet and this gets you interesting things. Getting back to the more complicated the ROS and the robot visualization in there is you're able to visualize the robot in ROS, not with the position that you send it to, but you can report back the position that it's actually at. You can see it move in real time because you're able to get that real time position back from the servo.
So are you planning to close this in ROS?
Oh yeah. Yeah, now that the hardware design is finalized, I'll take the design and move, actually my workflow this time will be to move the Fusion 360 model into Omniverse, articulate it, set up all the joints, and then export that Omniverse formatted robot back to Erdif. The challenge is there's a lot of detail in here. And Erdif models are generally very, very simple. So I need to find a way of simplifying the parts. Not that the computer can't render it, but there's no point where the graphics card could render 100 million polygons a second and make it look super awesome. The Erdif SPLs need to be vastly simpler. That's why I haven't figured it out yet.
Oh,
I wrote a bus servo driver for ROS. So
Oh yeah.
if you get there, yeah, I forget why, but
you had to write one?
yeah, either they didn't have one or I didn't like it or it was too slow or something, and so I wrote one.
Not for you. We'll be downloading.
Yeah, absolutely.
Right on.
Yeah,
So,
because you need, if you want this in ROS, you want a driver for this stuff in ROS,
yes.
ROS 2.
So instead of doing your timed out sleep, could you like just pull for 0 velocity and like change once it?
Absolutely. That's a very good point. If you wanted to be even, clever about it, because you could ask the servo, is it moving? Has it reached its target position? You could write a loop that instead of waiting for sleep 4, like I'm doing because I'm being super simple, is to have a loop that pulls the servo and it says, hey, are you still moving? Yes or no? If the answer is yes, sleep for a millisecond or 100 milliseconds and then try again. Yeah, now you're thinking like a serial bus servo guy.
Can
So
you write a loop that'll just make it go continuous? Just continuous. And what would happen? Yeah,
I'm not sure. Maybe during break you can try that. But yeah, these servos are capable of continuous operation. They use a magnetic encoder, so they're not limited like a traditional potentiometer. And they do accept continuous rotation velocity commands. So yeah, you do a lot of fun stuff with it. So to take this back home, there are 7 servos on each arm, and then there's 3 in the head of, let me go bring up the Alfie graphic. So there's 3 servos in the head because you can't cop your head to one side, then what's the point? There are
I think Alan likes this because it looks a little more like the Delta printer that we got. Got the same, like a one side of the Delta printer.
that's actually a Super Racer Delta printer.
It is, huh?
It's the lower cost one.
It's a 3D printer turned into a robot.
It is, it's like a one side of a 3D printer.
Or part of
a robot, yeah.
Yeah, so each one of these arms of 7 servos is connected to a general driver board with an ESP32 in the base, right? So there's 3 levels of computation happening in the robot. The ESP servo board, the driver boards communicate directly with the servos, right? And so you can run the hello world code and you can write the Arduino code to move, and then it works just fine. These servo drivers are connected over USB to it's like a Raspberry Pi IndyDrive building board that has 8 cores, 16 gigs of RAM. It's one of the beefiest versions I could find, right? So we're going to use ROS to facilitate the communication between the main computer and the ESP32 microcontrollers, right? So we're coming up with messages that look similar to this. For the movement, tell me where you want me to go, how fast what the acceleration is. There's a similar set of messages for the wheels as there are for the lights in the head. And then after that, what I'm calling brainstem code is all in the boilerplate. Then we can start writing some programs that make the robot come to life. So it took me about 2 months from, hey, this sounds like a cool idea, to burning my fingers for the last time with a soldering iron. Construction's complete. Maybe 2 weeks for the boilerplate brainstem code. I'm just calling it that because it's not code that does something. It's code that allows you to do something with it. And then things would get interesting. Based on the work and the progress with these heavy duty humanoid robots, I see no reason why some or all of that can't also be applied to an Alfie style robot. So the Aloha mobile platform is $37,000 as a kit from Frossen Robotics. This guy, if you subtract out the dead ends and the extra parts that I purchased, if you're like, oh my God, Alan, I want to build an Alfie, and I give you the bill of materials, it's about $2,100. So it's not super cheap, but it gets your foot in the door to play with some of the most exciting robotics topics and concepts and applications that I've seen since I was a kid. Yeah,
Got the microphone on the top. LiDAR
yeah,
or the.
yeah. So no LiDAR on this one. I'm using the depth camera from
Oh, yeah. Up the front
from the
panel.
feet. Yeah, which should give you enough information. And then yeah, the microphone on top, the little top hat, not only gives me raw audio, I believe it gives me filtered audio. Okay, so the Jim would keep me honest. As well as direct. All kinds of fun stuff. It was just a matter of integration. So this is the systems integration phase where I bolted everything together, and now I gotta write the code to make it work. So yeah, so that's all I've got for this week. I'll be here. We'll probably head back here after the break for lunch. I can answer any questions about Alfie or serial bus service.